We continue our review of infinite limit techniques by focusing on limits for functions at values where they have vertical asymptotes, namely at finite x values. However, the answer turns out to be plus or minus infinity. As usual, at this example for a limit, we're going to start by trying to evaluate the function at the particular value of 2, and we obtain 2 minus 5, which is negative 3, divided by 4 minus 4, which is 0. So if we focus on this particular form here, negative 3 over 0, we recall that 1 over 0 produces an explosion to plus or minus infinity, so we are dealing here with a vertical asymptote. In fact, if you get a non-zero constant over 0, this is the form that you want to be on the lookout for when you're dealing with this limit that produce an answer of plus or minus infinity and that induce for the graph of a function a vertical asymptote. Again, we want a non-zero constant over 0, different from the indeterminate form of 0 over 0, in which case the answer could be anything, including plus or minus infinity, but it could also be a finite limit and the answer could be 5, or the limit might not exist. So what is the technique in this case? Well, let's think about this graphically. We know now that this explosion to plus or minus infinity at x equals to 2 will give us a vertical asymptote of equation x equals to 2. The question is, however, what happens near the asymptote? Will the graph of a function, say to the right of 2, shoot up to positive infinity or down to negative infinity? And the same question is true to the left of 2. So this entire technique is going to rely on the following idea. We're going to pick a value very, very close to 2, and then we're going to evaluate it into the function. If the function value turns out to be a positive number, then that must mean the asymptote is shooting up towards positive infinity. If, on the other hand, when we evaluate, we obtain a negative number, then the function must be shooting down to negative infinity, so we have the answer to the limit is negative infinity. So let's start by writing down the limit to the left of 2 and the limit to the right of 2 of this particular function. And since we're trying to only determine the sign, I don't really care whether this is going to turn out to be plus 7 or plus 100. All I need is that it's positive or negative for that matter. So we're only interested in determining the sign of the expression. And for that reason, it is a lot easier to compute the sign of an expression if we look at the factored form of the expression. So instead of writing x minus 5 over x squared minus 4, we're going to factor first, and that's going to make our life easier. If you forget to factor, you're just going to have to deal with some very nasty computations. So try to remember to always factor when you compute these limits that produce plus or minus infinity as an answer. So we're first focusing on the limit to the left of 2 of this particular expression. So we pick a number very, very close to the left of 2, for example, 1.9. So we're going to take the number 1.9 and plug it into the expression and just focus on the sign of the expression. So 1.9 minus 5, I don't care the exact number, I just care about the sign. So I'm going to record that that turns into a minus. And then 1.9 minus 2 will give me another minus. 1.9 plus 2 will give me a plus. And now notice that I wrote these symbols. They're really only some meaningless symbols. They're not a number. And what I write to the right of the equal sign should be a number. But they're going to help me determine the sign of my limit. So minus, minus, and plus put together, just as with numbers, gives me positive. And I already know the answer will be infinity. I just needed to figure out what type of infinity it's going to be. So I figured it out. It was a positive expression. So for that reason, this limit turns into positive infinity. Similarly, give me a number to the right of 2. For example, 2.1, you want to be relatively close to 2, and that depends on the given scenario of your expression, but generally 2.1 is going to be sufficiently close. Let's evaluate now in this particular expression here. So 2.1 minus 5 gives us a negative number. 2.1 minus 2 gives me a positive number, and 2.1 plus 2 gives me a positive number. So put together, this gives me a minus, and then of course I have the infinity afterwards. So when I look to this particular asymptote at 2, what I realize is that at x equals to 2, the function values are shooting up to infinity to the left of 2, and they're shooting down to negative infinity to the right of 2. And this is the way the graph of the function holds. And of course, since the limit from the right does not agree with the limit from the left, we write that this limit does not exist. In general, limits whose answer turn out to be infinity do not exist. However, we often say that the limit is infinity to tell the reader more information about this limit, rather than just say the limit doesn't exist. It could not exist for a variety of reasons. So, infinite limits, by definition, do not technically exist, but we still nevertheless record them as positive or negative infinity in the scenario where we don't look at the one-sided limit, because the limit from the left of 2 and the right of 2 do not agree. We will write that the limit does not exist. Let's consider a second example. So let's compute the limit as x goes to 3 of x squared minus 1 over x squared minus 2x minus 3. When we plug in 3, we get 9 squared minus 1, which happens to be 8, divided by 9 minus 6 minus 3, which happens to be 0. So again, this particular form, which is indicative of this explosion to plus or minus infinity, gives us the idea that we are dealing for the graph of the function with a vertical asymptote at x equals to 3. So what we're going to do is look to the left and to the right of 3 to determine what happens with the behavior of this function. This is going to help us justify what happens with the limit here. So let's remember that we want to record the factored form of the expression. So x minus 1, x plus 1, and for the denominator x minus 3 and x plus 1. So let's copy the same thing here. We could of course cancel an x plus 1, but it doesn't really matter for our expression, so let's just leave it. So now we're going to pick a number to the left of 3. So let's say we are focusing on the number 2.9. And we're going to evaluate it in our expression to determine the sign. As I said, I already know the answer is infinity. I just need to determine whether it's positive or whether it's negative infinity. So plugging 2.9 in the first parenthesis, 2.9 minus 1 is plus, 2.9 plus 1 plus, 2.9 minus 3 is negative, 2.9 plus 1 is plus. So put together, this gives me minus infinity. In the scenario of being to the right of 3, I pick the number of 3.1, and when I evaluate, I get plus, plus, plus this time around, and plus again. So the answer overall will be positive infinity. So given that the limit from the left and the limit from the right does not agree, we have that the general limit does not exist. And more so, we've been able to determine the shape of our graph. So looking at the graph and the asymptote at x equals to 3, we've determined that to the left of 3, the graph shoots down to negative infinity, and to the right of 3, the graph shoots up to positive infinity, and we have the equation for my vertical asymptote x equals to 3. So again, when you recognize the form a non-zero constant over 0, we think of division by 0, which creates an explosion to plus or minus infinity, and we can simply visualize that we are dealing in fact with a vertical asymptote like we have here. The idea is to determine whether the graph shoots up to positive infinity or down to negative infinity, both to the right of 3 and to the left of 3. So for that reason, we compute the limit from the left and the limit from the right, and we do so by looking at the factored form and simply plugging in some values to the left and to the right of 3 to determine the sign, and therefore determine whether we're dealing with plus or minus infinity.